Webb telescope reveals the most distant star in the cosmos. In a monumental discovery that has redefined the boundaries of cosmic observation, the James Webb Space Telescope, JWST, has detected the most distant star ever observed, named Earendel. This star existed when the universe was just 900 million years old, its light taking over 13 billion years to reach Earth. What makes this discovery even more astonishing is that the star is now located approximately 28 billion light-years away, due to the expansion of the universe. This observation has given astronomers an unprecedented glimpse into the ancient universe, providing a crucial opportunity to study the early stages of star formation, galactic evolution, and the nature of the cosmos. Earendel's discovery marks a major leap forward in our understanding of the universe and the capabilities of modern technology to explore the depths of space. The findings highlight the critical role of the JWST in the study of the early universe and underscore the importance of cutting-edge space exploration in uncovering the mysteries of our cosmic origins. The James Webb Space Telescope, a revolutionary tool. Before delving into the discovery of Earendel, it is essential to understand the remarkable technology behind the James Webb Space Telescope, which has been heralded as one of the most significant advancements in astronomy. Launched on December 25, 2021, after years of development, Webb is the most advanced space telescope ever created, designed to exceed the capabilities of its predecessor, the Hubble Space Telescope. JWST orbits the second Lagrange point, L2, located about 1.5 million kilometers from Earth, where it enjoys an undisturbed view of the cosmos. Unlike Earth-bound telescopes or even those in low Earth orbit, Webb operates in a stable environment, free from atmospheric distortion and thermal interference. This location allows the telescope to observe deep space with unparalleled clarity. One of Webb's most groundbreaking features is its ability to observe the universe in infrared light. Unlike visible light, which can be blocked or scattered by cosmic dust, infrared light can pass through these obstacles, allowing Webb to observe objects that are hidden from other telescopes. Infrared observation is also crucial for studying the distant universe. As the universe expands, the light from the most distant stars and galaxies is stretched into longer wavelengths, a process known as redshift, shifting the light from the visible spectrum into the infrared. Webb's advanced infrared instruments make it ideally suited for detecting these faint, redshifted objects, providing a window into the distant past. At the heart of Webb is its massive primary mirror, which is composed of 18 hexagonal segments coated with a thin layer of gold. This mirror is 6.5 meters in diameter, making it more than twice the size of Hubble's primary mirror, and vastly increasing Webb's ability to capture light from faint, distant objects. The mirror's unique segmented design allows it to fold up for launch and then unfold once in space, a feat of engineering that has expanded the telescope's potential for deep space observation. The discovery of Earendel, unveiling the distant cosmos. The discovery of Earendel represents a scientific breakthrough that pushes the limits of human understanding of the cosmos. The star's name, Earendel, is derived from an Old English word meaning morning star or rising light, a fitting title for a star that illuminates one of the earliest epochs in the universe's history. Earendel was discovered in a region of the sky known as the sunrise arc, where the light from distant stars is magnified by an effect known as gravitational lensing. Gravitational lensing occurs when the gravitational pull of a massive object, such as a galaxy cluster, bends and amplifies the light from objects behind it, allowing astronomers to observe distant stars and galaxies that would otherwise be too faint to detect. In this case, the massive galaxy cluster WHL 0137-08 acted as a lens, magnifying the light from Earendel by a factor of over 1,000 times. This gravitational lensing effect was first predicted by Albert Einstein's general theory of relativity, and has been used by astronomers to study distant objects for decades. However, The discovery of a star as distant as Earendel represents a new frontier in the application of this phenomenon. Without the natural magnification provided by WHL 0137-08, Earendel's light would have been far too faint for even the powerful JWST to detect. The discovery of Earendel has shattered the previous record for the most distant star ever observed. Before Webb's discovery, the farthest star known was Icarus, observed by the Hubble Space Telescope in 2018. Icarus existed about 9.4 billion years ago, while Earendel existed over 13 billion years ago, pushing the boundaries of our cosmic horizon by billions of years. The significance of Earendel: a window into the early universe. The discovery of Earendel is significant for several reasons. First and foremost, it provides an unprecedented opportunity to study the early universe and the formation of the first stars and galaxies. By observing Earendel, astronomers can gain new insights into the conditions that existed when the universe was less than 1 billion years old, a period known as the epoch of reionization. During this time, the first stars and galaxies began to form, and the universe transitioned from being filled with neutral hydrogen gas to becoming ionized by the light from these early stars. Earendel's discovery opens the possibility that it could belong to the first generation of stars, known as population 3 stars. These stars are thought to have been composed almost entirely of hydrogen and helium, the two lightest elements, which were produced in the Big Bang. Unlike later generations of stars, which contain heavier elements, referred to as metals, in astronomical terms, population 3 stars would have been much more massive, hotter, and shorter-lived than stars we see today. Population 3 stars are considered the building blocks of the universe, as they were responsible for producing the first heavy elements through nuclear fusion. These elements, in turn, formed the raw materials needed to create planets, galaxies, and eventually life. However, no direct evidence of population 3 stars has ever been found, until now, perhaps. If Earendel is confirmed to be a population 3 star, it would provide the first direct evidence of these primordial objects and offer a rare glimpse into the earliest stages of cosmic evolution. Additionally, studying Earendel can help astronomers better understand the process of star formation in the early universe. The star's light can be analyzed using a technique called spectroscopy, which allows scientists to determine its chemical composition, temperature, and other properties. By comparing Earendel's characteristics to those of more modern stars, astronomers can gain valuable insights into how the first stars formed, how they differ from later generations of stars, and how they contributed to the evolution of the universe. How Webb made this discovery possible. The discovery of Earendel would not have been possible without the advanced technology of the James Webb Space Telescope. Webb's suite of instruments is specifically designed to observe the universe in infrared wavelengths, which is essential for studying distant objects that are highly redshifted. One of the key instruments that made the discovery of Earendel possible is the near-infrared camera, NIRCam. NIRCam is capable of detecting the faint infrared light from distant stars and galaxies, making it an essential tool for studying the early universe. Its sensitivity to infrared wavelengths allows it to see objects that are billions of light-years away, and its advanced optics provide a level of detail that was previously unattainable with other telescopes. In addition to NIRCam, Webb is equipped with the mid-infrared instrument, MIRI, which operates at longer infrared wavelengths and is designed to study the chemical composition of distant stars and galaxies. MIRI can analyze the light emitted by objects like Earendel to determine their chemical makeup, temperature, and other physical properties. This information is crucial for understanding the nature of the star and determining whether it is indeed a population 3 star or part of a later generation. JWST's large primary mirror also played a critical role in detecting Earendel. The mirror's 6.5-meter diameter allows it to collect more light than any other space telescope, making it possible to observe incredibly faint objects like Earendel. The mirror's gold coating enhances its ability to reflect infrared light, further increasing its sensitivity to distant objects. Gravitational lensing, a cosmic magnifying glass. As mentioned earlier, the discovery of Earendel was made possible by a natural phenomenon known as gravitational lensing. This effect occurs when a massive object, such as a galaxy cluster, bends and magnifies the light from objects behind it. In this case, the galaxy cluster WHL0137-08 acted as a cosmic magnifying glass, amplifying the light from Earendel and making it visible to JWST. Gravitational lensing is a powerful tool in astronomy, as it allows scientists to observe objects that would otherwise be too faint or distant to detect. The effect was first predicted by Einstein in his general theory of relativity, and has since been used to study a wide range of cosmic phenomena, from distant galaxies to exoplanets. However, the discovery of a star as distant as Earendel represents one of the most remarkable applications of gravitational lensing to date. Without the gravitational lensing provided by WHL0137-08, Earendel's light would have been far too faint to detect, even with Webb's powerful instruments. The lensing effect magnified the star's light by a factor of over 1,000 times, allowing astronomers to study it in unprecedented detail. Gravitational lensing also provides valuable information about the structure and composition of the galaxy cluster WHL0137-08 itself. By analyzing the way the cluster bends light, astronomers can learn more about the distribution of dark matter, the mysterious substance that makes up about 85% of the matter in the universe. Dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. However, its presence can be inferred through its gravitational effects on visible objects, such as the bending of light in a gravitational lens. The broader implications for cosmology. The discovery of Earendel has profound implications for our understanding of the universe, particularly in the areas of cosmology, dark matter, and the early stages of star formation. One of the most significant aspects of this discovery is the opportunity it provides to study the universe during the epoch of reionization, a critical period in cosmic history. During the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas, which absorbed light and made the cosmos opaque. As the first stars and galaxies formed, their intense ultraviolet radiation ionized the hydrogen gas, making the universe transparent to light. This process, known as reionization, marked the end of the cosmic dark ages and the beginning of the structured universe we see today. By studying stars like Earendel, astronomers can learn more about the process of reionization and how the first stars contributed to it. Understanding reionization is essential for piecing together the history of the universe and determining how it evolved from a featureless void to the complex, structured cosmos we observe today. In addition to its implications for the study of reionization, Earendel's discovery also offers new opportunities to study dark matter. Gravitational lensing, the phenomenon that made Earendel's discovery possible, is caused by the gravitational pull of dark matter in galaxy clusters. By studying the way dark matter bends and magnifies light, astronomers can learn more about its properties and distribution, providing new clues about the nature of this elusive substance. The future of star and galaxy exploration. The discovery of Earendel is just the beginning of what promises to be a new era of exploration in the field of astronomy. JWST is expected to continue making groundbreaking discoveries, pushing the boundaries of what we know about the universe, and providing new insights into its early history. In addition to studying individual stars like Earendel, Webb will also focus on finding and analyzing the earliest galaxies, some of which may have formed just a few 100 million years after the Big Bang. These early galaxies hold the key to understanding how the universe evolved from a hot, dense state to the structured cosmos we see today. JWST will also play a critical role in the search for the first supermassive black holes, which are thought to have formed shortly after the first stars and galaxies. These black holes likely played a significant role in shaping the evolution of galaxies, but their origins remain a mystery. By studying the early universe, Webb could provide new clues about how these black holes formed and grew to the enormous sizes we observe today. Conclusion: the James Webb Space Telescope's discovery of Earendel, the most distant star ever observed, marks a monumental achievement in the field of astronomy. This breakthrough not only sets a new record for the farthest star ever detected but also opens up new avenues for exploring the early universe and understanding the processes that shaped it. Earendel's discovery highlights the critical role of JWST in pushing the boundaries of cosmic observation and expanding our knowledge of the universe. As we continue to explore the cosmos with Webb, we can expect many more groundbreaking discoveries that will reshape our understanding of the universe and our place within it.